All right, so today we're going to be doing projectile motion part 3. So we're going to be looking at the last two cases. I actually added one more case at the end just for a bonus. So case 3 is similar to case 2. The only difference is that here we're launching off of the horizontal cliff with an angle, whereas for case 2 you were launching directly just horizontally off the cliff, so there was no angle here. So what this angle represents is that now you have two components for VI. So initial velocity, you have two components. So instead of just having VIX at the beginning, you're going to have VIX and VIY, right? So essentially it creates a triangle for your VI, right? So this is your VI, this is your VIX, and this is your VIY. So if you notice the difference is that for case 2, you only had your VIX and not your VIY just equal to 0, right? And then the rest of the diagram is similar to case 2. So let's get right into the case-based rules. So first things first, we have the delta YF. So any position within this diagram essentially can be calculated using this equation, right? This equation was built off of the fact that, or the assumption that we're trying to calculate the time for our final position. So if we were to set this to 0, right, and then calculate our time, so essentially to calculate the total flight, right? So total time of flight, you would use this formula, and you can rearrange this formula to calculate for different positions within the parabolic curve. So if you notice, this equation looks similar to a quadratic, right? Because it is a quadratic. So if you notice, it's exactly the same as the standard form ax squared plus bx plus c. And essentially, I've labeled here on the side the coefficients, right? So the a of x, right, which is the term 1/2 times a times delta t squared. And then you have b of x, which is the term VIY times delta t. And then you have your term c, which is h, right? So from here, we can extract the coefficients to then use a quadratic formula to calculate your total time of flight. Right, so this is the easiest way to do so when you are trying to calculate the total time of flight for your projectile in this case. And again, here I've listed the coefficients, so you can double check those. And then moving on, so let's say you want to find the time between, or the time at the max height, right? So the time right here, right? So if we were to label this point B, it would be from point A to point B, right? So let's say you want to find the time between point A to point B, you would use this formula. And this formula, if you notice, looks similar to the case-based rules for case 2. So if you haven't noticed by now, this case is extremely similar to case 2. So all of the rules that you can use for case 2, you can also apply here, right? And then again, similar to case 2, you can also use this formula to calculate your time from your max height to your final, right? So from point B to point C. So this is the formula you would use for that. And this is another derivation of one of the formulas that we've seen before. And this is the fully derived form. This is the fully derived form of that. So essentially, what kind of happens here is we're just rearranging for your delta t squared. And essentially, the reason why these are important, right, is because you can use these two values and add them together to then get your total time of flight, right? So if you don't want to do a quadratic equation, then this is another method to calculate your total time of flight, right? And then again, you can calculate your h using the same formula that I used for case 2. And if you haven't seen that already, you can check out my video for part 2, which is a video right before this one. And then another formula for this case is your delta dy max. So essentially, your formula for the highest position in your curve, right? So the highest position in your curve. So again, you're using your h, which is your initial height, so the height of the cliff, and then your vi, and then again your 2 times g, which is just 2 times acceleration, because g is equivalent to acceleration. So again, this is another formula that's very similar to one that's used in case 2, but these are the case-based rules for case 3. So let's get right into the example. So in this example, we have a projectile that is launched from the top of a 50-meter cliff with an initial velocity of 20 meters per second and an angle of 30 degrees above the horizontal. So again, like how I like to approach every single problem that we've done so far, my first step is always to draw myself a diagram that allows me to visualize what I'm reading, right? So in this case, I've drawn my horizontal here, right? So this would be my horizontal. This would be my cliff, right? So this would be my cliff, and I've labeled it as 50 meters because that's the initial height of the cliff. And then the angle would be here, and I've extracted this triangle and drawn it again here to show you how this triangle or VI would have a VIX component and a VIY component, right? So we're going to use this diagram, and then we're going to find the time of max height. So what does that mean? That means that at the max height, so at point B, what is the delta t, right? So what is the delta t? And then we're going to find the range, right? So what is the range? The range is the entire entire horizontal path that the projectile travels. So again, like how I approach every single problem, I write my givens and my unknowns first, and I highly recommend you guys do the same. Start with your givens and unknowns because it helps you track your solution as you go. So what am I given here? I'm given my VI, which is 20 meters per second at a 30-degree angle, and I'm given my initial height, which is h, or the height of the cliff, which is 50 meters. I need to find my delta t max. So in this case, delta t max, I've just made that into a kind of abbreviation to note that delta t max is equivalent to delta t at my max height. So at my max height. and then I need to find my r, or in other words, delta dx, right? So let's start with solving for the x and y components of vi. And remember, whenever you do have an angle for any type of velocity component, you always want to solve for your x and y components first because they will be useful for the rest of the question. So before you start anything, start by solving those x and y components. So here I've solved for vix and viy using trigonometry. So I've used the SOHCAHTOA that I've talked about in my previous videos. Again, you can check it out in Projectile Motion Part 1 and 2, where I've actually talked about the trigonometry. I will be releasing another trigonometry video more in depth soon. If you have any further questions about trigonometry, though, before that, you can always reach out. So I've gotten my VIX to be 10 root 3 meters per second and my VIY to be 10 meters per second. So next step, right? So after I've calculated that, the next step is to calculate the time at my max height. And what did we say was the time at your max height, right? We gave a formula for that in the k-space rules, which is delta t from point A to point B, right? So using this formula, right, we just plug it in. So our V is 20 and then sine of 30 over 9.81, right? So this gives us 1.02 seconds. This gives us 1.02 seconds. And now we're going to calculate the next part of it. So we're going to calculate the range, right? So essentially to calculate the range, however, right, if you notice, you need your delta t for the entire path of the projectile, right? So the first step before that is actually calculate your total time. And what do you need to calculate your total time? The formula that we talked about for your quadratic, right? So for your vertical position. So in this case, to calculate your total time, we set our final position to 0, right, because it hits the ground, and then we sub in our values for everything else. So your height is 50, your VI would be 10 because we're using VIY here, right? Since you're only calculating for vertical components here, you're going to use your VIY, not just your regular VI. So you plug in your VIY, and then you plug in your 1/2 acceleration. And again, this is this is 1/2 times negative 9.81, which is why this plus turns into a negative here. And then from here, it's just using the quadratic formula, right? So the quadratic formula is linked, labeled here. So you can see the quadratic formula here if you don't remember it. Once that's done, once the quadratic formula is noted, you can plug everything in. Now, here's the important part. When you use your quadratic formula and you solve everything out on your calculator, you will get two answers. You'll get one negative and one positive. Time, as you know, time cannot be negative, right? So it's impossible for time to be negative. Therefore, the correct answer is the positive, right? So you automatically know that you cannot have a negative answer, which is why your positive answer will be correct. So don't get confused thinking that there's two different answers. It's only one answer. It's just a positive answer. And then from there, you can just calculate your range, which this formula was talked about in part 2. It's just it's one of the case-based rules for case 2 and case 3. So this formula can be used to calculate range, which is just VIX times your total time. Again, you have your VIX to be 10 root 3, and you have your total time, which you calculate in the step above. And your final answer should be 75.69. So now that's done, we're just going to quickly go over. All right, so we're going to look at case 4. So this is kind of like a bonus case. The original series was only supposed to be 3 parts. However, I decided to make a fourth part that actually looks at the projectile motion when you have a vertical launch. So essentially, this is a very simple case where something is just launched either upward or just let go free falling, right, from the top. So essentially, you can either have something just being launched from the bottom, so ground level, or you can have something that's being dropped like this, so free falling, right? And then the case-based rules for these, right? So then first of all, an example for this would kind of be a rocket launching upwards. So the rocket launching upwards and then eventually coming back down would just be a vertical launch, right? Or another example would be if you let go of a ball outside of a window and then you just let it fall straight down, that would be a vertical launch, right? So that's free falling. So the case-based rules for these are pretty simple. We have the first case-based rule, which is just a kinematic equation for delta dy, right? So your position, your vertical position, essentially. And again, this case has no angle because there's no angle to be made here. So it's just your vi, right? And then we have your velocity at any time, right? So at any time within your path of travel, right? So here, you'll have different velocities, so v1, v2, v3, and those velocities can be calculated using this formula here. And then you have your delta dy max, which is essentially the highest, right? So the highest point that your projectile will reach, right? So the peak altitude. And then you have your delta t max, which again is just an abbreviation for the time, right? So the time at when the projectile reaches the highest point in its altitude, right? And then you have your final one, which is delta t total, right? So that's essentially just 2 times delta t max because in a vertical launch, something is just going up and then coming back down. So if the time to go up, right, is delta t max, then the time to go down is just delta t max plus another delta t max, right? So in other words, 2 times delta t max. So let's get right into the example for this one. So we have an example saying a firework is launched straight up, right? So it's launched straight up into the air with initial velocity 60 meters per second. Calculate dy max and delta t at dy max, right? So again, let's draw a diagram, right? This one is a pretty simple diagram, but it's always important to draw a diagram so you can visualize the problem. So we've drawn a diagram here and we've labeled what we kind of need, right? And then we can start with our givens and unknowns, just like every other problem. If you haven't watched the other 3 parts, I highly recommend you watch the other 3 parts because I go over why it's important to use those givens and unknowns to track your solution. So for our givens, we're given one thing, the vi, and then for our unknowns, right, we have 2 unknowns. So this may look daunting at first because we're only given one thing, but we have 2 unknowns, right? But as we continue with the case-based rules, we'll understand why this is actually a very simple problem. So the next part is calculating delta d max, right? So delta dy max, right? In other words, delta dy max. And as we said, right, we have the case-based formula for this, right, which we derived up here, right? And again, this formula is given, so it's a case-based rule. I will be posting another video of how these formulas are actually derived. So if you don't understand the derivation of it, then stay tuned for that video. Or you can message me, and then I'll be happy to help you understand which formula that you're having trouble with. So this formula we're using for delta dy max, we sub in our 60 for vi, and then again we just have 9.81 for acceleration, right? So when we have this, right, when we do this, we get it's a pretty simple, straightforward solution on your calculator. You can just plug it in, 60 squared over 2 times 9.81. This will give you 183.49 meters. So that means that if you launch the firework directly up, right, the highest it goes is this amount of meters. So it only goes up 183.49 meters before it comes falling back down, right? Now, the next part of the question is to calculate your delta T max, right? So in other words, the time at 183.49 meters, right? And again, this is a very simple formula that we had, which is just VI over gravity, right? So in this case, it's just 60 over 9.81. So the time at the top or the peak altitude is 6.12 seconds. If you do have any further questions about any of the previous cases that I've talked about so far, or any of the other 3 parts, you can message me or reach out. If you have any other specific problems you want me to do, then again, you can message me and reach out. I'll be happy to help and post videos on those. And again, follow for more, and thank you.